In today's lesson, we're going to talk about related rates. A related rate word problem involves finding a rate at which a quantity changes by relating it to other quantities whose rates are known. These problems are similar to optimization problems in that we are going to need to take derivatives. That's where the similarity ends. In related rate problems, the derivative is crucial not only to finding the solution, but in also setting up the equation and relating the variables. Most of these problems involve implicit differentiation and the variables, which are often dependent on other changing variables such as time. So oftentimes I may have an equation with both x and y in it, but sometimes there is an unexplicit t for time that I'm going to need to take my derivative with respect to. To solve a related rate problem, the first thing we want to do is identify the known variables, including the rates of change. Okay? That means including the derivatives. So sometimes maybe I know that I have a height and a length, and I know the rate that the height is changing, and I want to try and find the rate the length is changing. Okay? So I need to know both the h and the l, but I also need to know dh dt and dl dt. Okay, so I'm going to construct an equation relating the quantities whose rates are known to the quantity of the rate to be found. And oftentimes you're going to want to use pictures or known formulas. Pictures, often things like your triangles using Pythagorean theorem to relate your sides, or known formulas like maybe your revenue equaling price times quantity. Differentiate both sides of the equation implicitly with respect to the changing variable. Again, in most cases, our changing variable will be time, and so we're going to want to take everything, derivate everything with respect to time. Then what we'll do is we'll substitute the known rates and quantities into the equation and solve and state the solution. Okay. Some common pitfalls or common errors to related rate problems. One of the biggest errors is not having a complete equation. And that sounds hard to do if you're trying to solve an equation, but oftentimes people will come up with a function, and so they'll have something like your revenue equals price times quantity, and they'll worry about the price and quantity side. But again, you have to have a full equation, so you're going to need to know the revenue as well, or some relationship of the revenue. Okay. Relating quantities to rates instead of rates to rates, or quantities to quantities. And that's just a fun bunch of words to say. But all I mean there is, again, if I'm thinking of in terms of triangles or setting up my variables, one of the biggest errors is, for example, one in which I'm looking at two cars moving in different directions, and instead of relating their distance, I'm relating their miles per hour. And so you want to make sure you're relating like quantities to like quantities. Incorrect derivations. Okay. Again, here all of your derivatives in related rate problems are going to be done implicitly. So you can't just take the derivative of x squared and say it's 2x. It is always going to be a 2x dx dt, or dx d something. It's always with respect to some unknown variable or changing variable. Okay. And then last, plugging in values prior to derivating. I put this as number 4, but this is probably the most common error. Many people are so used to working with functions that are in terms of one variable, and for related rates, this is the first time you really have to get away from that. If you start trying to plug in so that you only have one variable, then you end up taking derivatives of things that go to 0, and it doesn't make much sense in terms of the rate problem. Okay? So make sure you plug in the variables or the values only after you've derivated. Okay? So in our first example, we're going to look at a common ladder problem that you'll see with a lot of related rate problems in any calculus class. Okay, so we have a 10-foot ladder that's laying against the side of a building, and the base of the ladder is moving away from the building at a rate of 2 feet per minute. What is the rate at which the top of the ladder is moving down the side of the building when the base of the ladder is 3 feet away from the building? Okay. So this is one in which probably a picture would help us formulate an equation that will relate all of our variables and all of our rates. Okay. So in this case, let's say here's our building. Okay, and we've got this ladder. My funny looking ladder. Leaning against it. So there's kind of what our picture looks like. We want to put our information on the picture so we can relate the variables. So we know that the ladder is 10 feet. And obviously that is not a changing quantity. That's going to stay constant. And we are trying to find when it's 3 feet away from the building, moving away at a rate of 2 feet per minute. Okay. We want to know the rate the ladder is moving down the side of the building. Okay. So in this case, again, we need to set up an equation. So we've got 3 sides of a triangle, and again, we can think of it as a right triangle. So here, the first thing I'm going to do is I'm going to label my sides. I'm going to call the base here X. I'm going to call this side over here Y, and I'm going to call this side over here H. And I'm picking variables as I like them, but you can pick your variables to be anything you want. If you'd rather call this base and height and diagonal, so BH and D, that's fine. But label your variables. Okay? So if I look at my equation, my relationship between my variables is just the Pythagorean theorem. So x squared plus y squared has to equal h squared. Okay? Now, in order to solve a related rate problem, again, once I have my equation, I want to find all my known and unknown quantities. Okay? In this case, because I have 3 variables, I'm going to have 3 different rates. Notice my rates here are some unit of distance with respect to a unit of time, but time doesn't show up in my equation here. That means all of my variables are implicit functions of time. So here, when I'm listing my known and unknown variables, we know that x is going to be 3 feet. We know h is going to be 10 feet. And it doesn't look like I know y, because I don't have that information. But again, I have a relationship so that I can solve for y. We know y is going to be the square root of h squared minus x squared. So 100 minus 9, which looks like the square root of 91. Okay? Again, with all the variables, I should have corresponding rates with them. So in this case, again, a unit of distance with respect to a unit of time. I know dx dt, that's given to me. It's moving in the positive direction, 2 feet per minute. dh dt, well, if we think about it, the rate the ladder is changing with respect to time, that's going to be 0. It's a constant, fixed value. So in this case, we're not going to put anything in. And then dy dt, well, that's what we're looking for. Okay? So I'm going to set up my equation and find the relationship between all the variables and their corresponding rates. Once I have that information, now I can actually solve my related rate problem. So I'm going to take my original equation and I'm going to derivate it. And again, I'm derivating with respect to time. So 2x dx dt plus 2y dy dt is going to be 2h dH dt. Okay. Now that I have my related equation, my rate equation, I can go ahead and plug in my variables. And again, notice I'm only plugging in after I've taken the derivative. Okay. So we have 2 times 3 times my dx dt plus 2 times my y, which was square root of 91, times dy dt, which is what we don't know, so I'm going to leave that as dy dt. And this is going to equal 2 times my h times my dH dt. Now it's just a matter of solving. So 12 plus 2 square roots of 91 dy dt will equal 0. I'm going to move the 12 to the other side. And divide out. And again, you should go ahead and rationalize. And put in your units. Okay. So in this case, this is saying my y value, or the height of my ladder on the building, is changing with respect to time at a rate of -6 square roots of 91 over 91 feet per minute. And again, you can plug that into a calculator to get a decimal. And we should make sure that it makes sense. In this case, it does. If I look back at my picture over here, we can see that as the ladder moves out, the top of the ladder is going to move down the building. So that's going to be in the negative direction. So that makes sense. In this next example, we're going to look at a slightly different type of related rate problem, one in where it's not so much geometry, but it's more based on the formula. Okay. So in this example, the cost in dollars of manufacturing X number of high-quality computer laser printers is given by this equation, 15x to the 4/3 plus 54x to the 2/3 plus 600,000. Currently, the level of production is 1,728 printers, and that level is increasing at a rate of 350 printers each month. We want to find the rate at which the cost is increasing each month. Okay. Now again, the first look at this, it doesn't quite look like a related rate problem. It looks very similar to the setup that we've seen in many other problems. But again, the key, the reason we know that it's a related rate problem, is because not only are we talking about rates of increase or finding rates, but the variables here, so in this case C and X, are in terms of the unknown variable time. Okay? So in this case, there's not really a picture we can draw. If we look at our problem, our equation is already given for us. So, C of X equaling 15x to the 4/3 plus 54x to the 2/3 plus 600,000. This is the equation that we're going to relate. Now again, before we take derivatives and start plugging things in, we need to know what our known and unknown variables are. Okay? So over here, I'm going to go back and write those. So we have two variables. We have C and we have X. X we're given. We know the number of printers currently is 1,728. And we can find the cost. That's not going to be pretty, but we can plug it in. This is going to be basically C of 1728. Okay. So we need two different rates. We're going to need dC dt and dx dt. Okay. And in this case, dx dt is the thing we're given. We know that the level of increase for the number of printers is 350 per month. And dC dt is what we're looking for. Okay. Now I want to point out here, notice I didn't actually find C of 1728, and that's okay, you'll see why in just a moment. But if I did need that value, I know I just need to plug it in there and I can actually find it. Okay. So now that we've got our variables, our known and unknown, let's go ahead and take our derivative. Well, C of x is just C. Derivative of that is just going to be dc dt. Over here, looking at our derivative, we'll bring down our power, so we'll get 20x to the 1/3. Notice there's a dx dt in there. I'm going to hold off writing that. Plus, bringing down the 3, looks like 18 times 2 is 36x to the negative 1/3, and the 600,000 goes away. Because I'm taking these derivatives with respect to time, both of them will have a dx dt, so I can just put that at the end. And that's the nice thing about an explicit function. If I have a function, one side I can just treat kind of normally and then throw that rated derivative at the end. So now that I have this, notice in my equation here, I don't actually need this C of 1728. So I can just plug in the derivatives and the x values and solve. So dc dt is what we're looking for. Nicely, that's on one side of the equation by itself. 20 times, we'll plug in that 1728 plus the 36. Again, 1728. That's to the negative 1/3. And then that whole thing is going to be multiplied by 350. And nicely, I've kind of looked at this ahead of time. We can go ahead and simplify. So nicely, I went ahead and done this ahead of time, and we'll find that dc dt will turn out to be 85,050. Okay. Now again, this number actually means something, and so we can go back to the rate to determine what the units are going to be. So dc dt, C is our cost, so that's in dollars, and T is our times in month. So this means that the cost is increasing by $85,050 per month. So let's look at one last example of related rates. In this example, the demand for a certain product is currently 1,000 units, and it's increasing at a rate of 10 units per week. The price for each unit is currently $5. We want to find two different things. We want to find the rate the revenue is changing if the price is decreasing by $1 per week, and we want to find the rate at which the price would need to change for the revenue to remain constant. So to start out, we're going to use basically the same equation for both of them. If we look, we are given that the demand for a certain product is currently 1,000 units, and that the rate it's increasing per week, so again there's that implicit function of time, is 10 units. And we're told that the price for each unit is currently $5. And for part A, we want to find the rate we know that the price is increasing by a negative $1 per week, or decreasing by $1 per week. Now, in our question here, this gives us a third variable. We're trying to find the rate the revenue is changing when this is happening. So this means I should also have a variable for R. Okay? And this is where our equation is going to come from. So based on the information there, there's not really an equation explicitly stated, but if we look at our variables that are relating, we have a price and a quantity, and we're looking for revenue. So we know revenue equals price times quantity, which means in this case, our R is going to be $5,000, and dRdt is the thing we're looking for. Okay. So using this equation, we know that dRdt, so taking our derivative everywhere, is going to be, well, here we've got a product rule. Doesn't quite look like that, but again, if you think it's with respect to time, we would get the derivative of the first, which is just 1. So Q dp dt, so again, we've got to take it implicitly, plus P times the derivative of Q. dRdt is what we're looking for. Q we have, Q is 10,000, or sorry, 1,000. Plugging in our variables, dp dt is -1, P is 5, and dq dt is 10. Okay. So, looking at this together, dRdt is going to equal -1,000 plus 50, or -950. Again, to put our units on this, we need to remember what these things mean. So revenue is usually in dollars. Let's just rewrite it. So the revenue is decreasing, that's the negative, by $950. Our unit of time here is in weeks. So $950 per week is what the revenue is going to decrease at. So let's look at part B. So in this case, we're going to have a very similar setup, except now we want to find the rate at which the price needs to change for the revenue to remain constant. Okay. So we're again going to start with our different variables. So we know Q is 1,000, and we know the rate that the quantity is changing with respect to time is still 10 units. We have our price is $5, and the rate that the price is changing with respect to time, well, that's what we're trying to find in part B. And again, we're looking for when the revenue remains constant. So again, our revenue, we can think R equals P times Q. So revenue is going to be 5,000. And here, the rate it's changing, well, we want it to remain constant, meaning there is no change. So in this case, we want dRdt to be 0. So again, we'll do the same thing. So taking our derivative implicitly, dRdt is going to equal derivative of P, which is just dp dt, times Q, plus P times dq dt. Okay. Again, now that we have the derivative, we can plug in our quantities. So dRdt we know is 0, we want that to remain unchanged. Q, again, is 1,000. dp dt we don't know. P is 5, and dq dt is 10. Okay. So we just need to solve this equation for dp dt. So, -50, we'll look at like 1,000 dp dt. We'll go ahead and divide out. looks like -1/20. Or if we're going to put that back in terms of a decimal, negative, oops, it's -0.05. So what does that mean? It means, I'll write it over here, for the revenue to remain constant, the price will decrease by 5 cents per week. And again, using our dp and dt, using those variables, we can determine the units on this. So again, price is in dollars, or in this case cents, and time is in leaks.